mission. TESS was expected to detect approximately 1,250 transiting exoplanets orbiting the targeted stars throughout the 2-year primary mission, as well as an additional 13,000 transiting planets orbiting the stars in the TESS fields would observe. TESS had identified 2,601 candidate exoplanets as of April 5, 2021, with only 122 confirmed. After the primary mission concludes, data from the primary task will be used to search for planets, while the extended mission will collect additional data. Discoveries. Current mission results as of November 18, 2021. TESS discovered 172 confirmed exoplanets, with over 5,000 candidate planets still awaiting confirmation or rejection as false positives by the scientific community. TESS team members include the Massachusetts Institute of Technology, the Kavli Institute for Astrophysics and Space Research, NASA's Goddard Space Flight Center, MIT's Lincoln Laboratory, Orbital ATK, NASA's Ames Research Center, the Harvard-Smithsonian Center for Astrophysics, and the Space Telescope Science Institute. TESS began science operations on July 25, 2018. The observation of comet C2018N1 was the mission's first announced discovery. The first exoplanet detection announcement was made on September 18, 2018, with the discovery of a super-Earth in the Pi Mensae system orbiting the star every 6 days, adding to a known super-Jupiter orbiting the same star every 5.9 days. On September 20, 2018, the discovery of an ultra-short period planet, slightly larger than Earth, orbiting the red dwarf star called the LHS 3844 was announced. LHS 3844b was one of the shortest known orbital periods at 11 hours. It travels 932,000 kilometers to orbit its star, 579,000 miles. LHS 3844b is also one of the closest known exoplanets to Earth, with a distance of 14.9 parsecs. TESS's third discovered exoplanet is HD 202772ab, a hot Jupiter orbiting the brighter component of the visual binary star HD 202772. Located in the constellation Copernicus at a distance of about 480 light-years from Earth. On October 5, 2018, the discovery was made public. HD 202772ab orbits its host star every 3.3 days. It is an inflated hot Jupiter and a rare example of a hot Jupiter orbiting an evolved star. It is also one of the most strongly irradiated planets, with an equilibrium temperature of 2,100 degrees Kelvin, 1,830 degrees Celsius, or 3,320 degrees Fahrenheit. TESS made its first discovery of an Earth-sized planet on April 15, 2019. HD 21749c is a likely rocky planet that orbits the K-type main sequence star HD 21749 in about 8 days. The surface temperature of the Earth is estimated to be 427 degrees Celsius. After 1 year of operation, the southern portion of the survey was completed on July 18, 2019. It now turns its cameras to the northern sky. As of now, it has discovered 21 planets and has over 850 candidate exoplanets. The discovery of the young exoplanet DS Tuck-Ab HD 222259ab was announced in a paper on July 23, 2019. TESS first observed the planet in November 2018 and was confirmed in March 2019. The young world is more significant than Neptune, but smaller than Saturn. The system is bright enough to pursue radio velocity and transmission spectroscopy. The discovery of exoplanets around the M-type dwarf star GJ357 at a distance of 31 light-years from Earth was announced on July 31, 2019. TESS directly observed the transit of GJ357b, hot Earth with an equilibrium temperature of around 250 degrees Celsius. Ground observation and data analysis led to the discovery of GJ357c and GJ357d. While GJ357b and GJ357c are too close to the star to be habitable, GJ357d is on the outskirts of the star's habitable zone and may have habitable conditions if it has an atmosphere. With at least 6.1 ME, it is classified as a super-Earth. TOI 700d, the first Earth-size exoplanet discovered by the TESS, was announced by NASA on January 6, 2020. The exoplanet orbits the star TOI 700 in the Dorado constellation, which is 100 light-years away. TOI 700b, another Earth-sized planet, and TOI 700c, a super-Earth, are the other planets in the TOI 700 system. This system is unique because the big world is between the two more minor planets. It is currently unknown how this planet arrangement came to be, whether the planets formed in this order or if the more extensive world migrated to its current orbit. The discovery of TOI 1338b, the first circumbinary planet discovered with TESS, was announced on the same day. TOI 1338b is roughly 6.9 times the size of Earth, or approximately the size of Neptune and Saturn. It is located 1,300 light-years away in the constellation Pictor. The stars in the system form an eclipsing binary, which occurs when the stellar companions circle each other in our field of view. One is about 10% more massive than our Sun, while the other is cooler, dimmer, and only 1/3 the mass of our Sun. TOI 1338b's transits are irregular, occurring every 93 to 95 days, and vary in the depth and duration due to the orbital motion of its stars. TESS only detects transits crossing the more giant star. Transits traveling the smaller star are too faint to see. Although the planet transits irregularly, its orbit has been stable for at least 10 million years. However, the angle of the orbit to us changes enough that the planet transit will stop in November 2023 and resume 8 years later. On January 25, 2021, a team discovered and validated 4 extrasolar planets, 1 super-Earth, and 3 sub-Neptunes, hosted by the bright, nearby Sun-like HD 108236. The 2 high school students, Jasmine Wright, 18, of Bedford High School in Bedford, Massachusetts, and Kartik Pinglay, 16, of Cambridge Ringe and Latin School in Cambridge, Massachusetts, are said to be the youngest people in history to discover a planet, let alone 4. NASA announced in March 2021 that TESS discovered 2,200 exoplanet candidates. TESS had identified over 5,000 candidates by the end of 2021. On May 17, 2021, an international team of scientists, including researchers from NASA's Jet Propulsion Laboratory and the University of New Mexico, reported and confirmed by a ground-based telescope the Space Telescope's first discovery of a Neptune-sized exoplanet, TOI 1231b, within the habitable zone. The planet revolves around a nearby red dwarf star in the Vela constellation, 90 light-years away. With an emphasis on infrared astronomy, the James Webb Space Telescope, or JWST, is a space telescope. Because it is the most powerful telescope ever sent into orbit, it will be able to observe objects that the Hubble Space Telescope cannot, because they are too ancient, far away, or faint. Watch this space for updates on the James Webb Space Telescope. Background: the James Webb Space Telescope, or JWST, is expected to enable a wide range of astronomical and cosmological investigations, such as observation of first stars and the formation of first galaxies, as well as detailed atmospheric characterization of potentially habitable exoplanets. JWST was launched from Kourou, French Guiana, on a European Space Agency, or ESA, Ariane 5 rocket in December 2021, and entered orbit in January 2022. As of June 2022, the telescope is undergoing instrument mode check. Once operational, which is expected around the end of June 2022, JWST will take over as NASA's flagship astrophysics mission from Hubble. The first official science image release event has been scheduled for Tuesday, July 12, 2022 at 10:30 a.m. Eastern Daylight Time, USA. NASA, ESA, and the Canadian Space Agency work together to develop JWST. Northrop Grumman will be the main contractor. The Space Telescope Science Institute in Baltimore runs JWST, and the NASA Goddard Space Flight Center, or GSFC, in Maryland oversaw telescope development. The telescope bears the name of NASA Administrator James E. Webb, who oversaw the Mercury, Gemini, and Apollo programs from 1961 and 1968. In contrast to Hubble, which observes in the near-ultraviolet, visible, and near-infrared 0.1 to 1.7 micrometers spectra, JWST will operate in a narrower frequency range, from long-wavelength visible light, red, to mid-infrared, 0.6 to 28.3 micrometers. To observe faint infrared signals without interference from other sources of warmth, the telescope must be kept extremely cold, below 50 degrees Kelvin, 223 degrees Celsius, 370 degrees Fahrenheit. It's in a solar orbit near the Sun-Earth L2 Lagrange point, about 1.5 million kilometers, or 930,000 miles, from Earth, where its 5-layer kite-shaped sunshield protects it from the Sun, Earth, and Moon's heat. Development began in 1996 with a $500 million budget and an initial launch date of 2007. A major redesign in 2005, a ripped sunshield during a practice deployment, recommendations from an independent review board, a threat to cancel the project by the United States Congress, the COVID-19 pandemic, and problems with the telescope itself all contributed to the many delays and cost overruns that occurred. The media, scientists, and engineers all commented on the launch's high stakes and the telescope's complexity. Construction was completed in late 2016, and years of extensive testing preceded the launch. The total cost of the project is now expected to be around $9.7 billion. Features: the mass of the James Webb Space Telescope is roughly half that of the Hubble Space Telescope. The JWST's primary mirror is 6.5 meters, or 21 feet in diameter, and is made up of 18 separate hexagonal mirrors. The polished area of the mirror is 26.3 meters, or 283 square feet, with the secondary support struts obscuring 0.9 meters, or 9.7 square feet, for a total collecting area of 25.4 meters, or 273 square feet. This is more than 6 times larger than Hubble's 2.4 meter, or 7.9 foot diameter mirror, which has a collecting area of 4.0 meters, or 43 square feet. The mirror is gold-coated for infrared reflectivity and durability. The primary purpose of the JWST is to conduct research in the near-infrared region of the electromagnetic spectrum, but, depending on the instrument, it can also detect orange and red visible light, in addition to the mid-infrared region. It has the ability to detect things up to 100 times fainter than Hubble, and objects from considerably earlier in the history of the cosmos, dating back to a redshift of Z20, about 180 million years cosmic time after the Big Bang. In comparison, the first stars are thought to have formed between redshifts Z30 and Z20, 100 to 180 million years cosmic time, and the first galaxies may have formed around Z15, about 270 million years cosmic time. Hubble can only see back to the very early reionization, around Z11.1, galaxy GN-Z11, 400 million years cosmic time. Location and orbit. The James Webb Space Telescope is now traveling in a halo orbit around the Sun-Earth L2 Lagrange point in space. This point is located around 1,500,000 kilometers, or 930,000 miles beyond the Earth's orbit around the Sun. As it revolves, its actual position shifts between a distance of 250,000 kilometers, 160,000 miles, and 832,000 kilometers, 517,000 miles, from L2, which keeps it clear of shadows cast by the Earth and the Moon. In comparison, Hubble orbits 550 kilometers, or 340 miles, above Earth's surface, and the Moon is approximately 400,000 kilometers, or 250,000 miles away. Objects that are located close to this Sun-Earth L2 point have the ability to orbit the Sun in synchrony with the Earth. This enables the telescope to keep a roughly constant distance from the Sun, Earth, and Moon while keeping its one-of-a-kind sunshield and equipment bus oriented continuously towards these celestial bodies. Even the smallest temperature shifts caused by Earth and Moon shadows, which have the potential to affect the structure, can be avoided by the telescope thanks to its wide orbit that avoids shadows. This allows the telescope to block incoming heat and light from all 3 bodies at the same time, allowing it to continue receiving uninterrupted solar power and Earth communication on its side that faces the Sun. This arrangement keeps the spacecraft's temperature constant and below the 50 degrees Kelvin, or 223 degrees Celsius, 370 degrees Fahrenheit, required for faint infrared observations. Mission. The James Webb Space Telescope has 4 primary objectives: to look for light from the universe's first stars and galaxies after the Big Bang, to comprehend star formation and planet formation, to investigate galaxy formation and evolution, to investigate planetary systems and the origins of life. These objectives can be accomplished more effectively by observing in near-infrared light rather than visible light. As a result, unlike the Hubble telescope, the JWST's instruments will not measure visible or ultraviolet light. but will have a much greater capacity for infrared astronomy. JWST will be sensitive to wavelengths ranging from 0.6 to 28 micrometers, corresponding to orange light and deep infrared radiation at around 100 degrees Kelvin, or 173 degrees Celsius. JWST could be used to gather data on the dimming light of KIC 8462582, a star discovered in 2015 with some unusual light curve properties. In addition to this, it will be able to detect methane in the atmosphere of an exoplanet, which will enable astronomers to evaluate whether or not the methane represents a biosignature.
It will be 1.5 million kilometers, or 1 million miles from Earth at what is known as the second Lagrange point, or L2, for the James Webb Space Telescope, which will be 1.5 million kilometers or 1 million miles away from the Sun. This orbit is unique because it allows the telescope to track the Earth as it revolves around the Sun. Because of this, the telescope is protected from the Sun and Earth's heat and light by the enormous sun shield on the satellite and the Moon. Infrared light, which may be perceived as heat, is the primary focus of Webb's research. The telescope must be insulated from bright, hot sources since it will study extremely weak infrared emissions from distant objects. The satellite itself is included in this. The sun shield protects the spacecraft's delicate mirrors and equipment from the Sun, Earth, and Moon. A tremendous temperature differential exists between the telescope's hot and cold sides. You can boil water on the hot side and freeze nitrogen on the cold side. The telescope will be tested at 225 degrees below 0 degrees Celsius, minus 370 Fahrenheit. Sun shields are only effective when the Sun, Earth, and Moon all point in the same direction. Otherwise, they'll only provide the telescope with the equivalent of SPF 1 million sunscreen. So the telescope will be located at Lagrange point 2. The three-body problem was solved by Joseph Louis Lagrange, an 18th century mathematician. Is it possible for three bodies to circle each other and maintain their location relative to each other in a stable configuration? 5 possible solutions to this puzzle have been found, and they're known as the 5 Lagrange points in honor of their discoverer. An object's centripetal force is equivalent to the gravitational attraction of a massive mass at Lagrange points. The L4 and L5 points form no equilateral triangles. Instead, they form a straight line from L1 to L5. The Lagrange point, L1, is 1.5 million kilometers from Earth and has hosted several solar observatories such as Discover, Wind, and SOHO. WMAP, Herschel, and Planck have all been in orbit at the Sun-Earth L2 point, where Webb will be stationed. One of these 5 points makes it easier for an object like a spaceship to maintain its position relative to the other 2 bodies, like the Sun and the Earth. In reality, the orbits of L4 and L5 are self-stabilizing, meaning that nothing has to be thrown into them to keep them in place. The L4 and L5 locations on the Sun-Earth axis contain several tiny asteroids. There are metastable places in the solar system, which means that unless they are kept in place, things around these points will drift away into their orbits around the Sun. This is why L4 and L5 do not gather items. What if Webb is circling the Sun at a distance that is greater than the distance between Earth and the Sun? Usually, yes, but the balance of the combined gravitational attraction of the Sun and the Earth at the L2 point ensures that Webb will keep up with the Earth as it orbits around the Sun. At this time, the gravitational forces of the Sun and Earth are strong enough to maintain a spacecraft in orbit around L2 with comparatively minimal rocket fuel. Webb will circulate around L2 rather than being routed to the ground at L2. It's hard to believe, but Webb's orbit around the Earth is about the same size as the Moon's orbit around our planet. Due to Webb's long-duration orbit, the telescope will never be obscured by Earth or Moon shadow. Webb, unlike Hubble, will offer an unobstructed vision that will enable scientists to work around the clock. We can easily communicate with Webb because of its location at L2. We can communicate with it when the Earth spins using the Deep Space Network, which has 3 massive antennas on the ground in Australia, Spain, and California. Webb uses the DSN to uplink and downlink data up to twice daily during ordinary operations. The observatory can carry out series of instructions such as pointing and making observations on its own. This institute typically uploads a week's worth of commands all at once and makes changes as often as is necessary. At L2, Webb will take around 30 days to reach the start of its orbit, a quarter of the way there. However, it will only take 3 days to reach the Moon's orbit. Okay, getting Webb into an orbit around L2 is like trying to climb a hill by pedaling a bicycle aggressively just at the beginning of the climb, creating enough energy and speed to ride the rest of the way up the hill and barely make it to the summit. Instability exists at the L2 axis. These locations are known as Lagrange points, and they are the places where the Earth and Sun's gravitational forces are equal to each other. The Earth and the Sun line up with 3 of the points. They're referred to as L1 through L3 in this context. It's referred to as L4 and L5 because they create an equilateral triangle with the Earth and the Sun. The last 2 points are sturdily anchored in the ground. If you put anything there, it will behave like a ball at the bottom of an empty eggshell, rolling up the shell somewhat before returning to its original position in the middle. It's no longer possible for it to sit stationary anymore. Even in the context of the L2 point, there is no evidence of this. At least in the plane of the Earth-Sun system, the L2 point is unstable, as I said before. Then it might be that it's stable in a direction that's orthogonal to the plane. There's no other way to explain how the L2 point was so readily orbited. In addition, it must effectively circle the Sun like everything else. The Lagrange points are where you may achieve this, and you want to be able to communicate with it at all times. As a result of the fact that the sum of the parts is 0, gravitational forces such as those of the Sun, the Earth, and the centrifugal forces play a role. The Lagrange points are where the vectors cancel each other when drawn correctly. Put another way, the net force on each one is 0. However, even a little force, such as a planet's gravitational pull, may be enough to destroy it. The L4 and L5 points are now steady. The probe will be pushed back to the center by the combined force of the 3 forces described above, even if the knock is modest. It resembles a ball at the bottom of the valley in size. Forces at work pull the object back to the center even if it is pushed slightly out of place. Thus, it becomes steady. The 3 factors are in play when it comes to Lagrange points. Using them stabilizes L4 and L5. L2 is steadier though. Because of this, I'm stumped as to how they plan to orbit it. The instability may be just superficial or weak. For those who are new to Voyager 1, let's controls the spacecraft's thrusters and maintains a high-gain antenna pointing towards Earth so that the information about the interstellar medium continues to flow back to Earth. With the signal strength and absence of fault protection activation, the team can confidently say Voyager and the outer world.